So we're going to talk here about muscle recruitment and how muscle recruitment will inevitably lead to muscle fatigue. This is where we have to remember some of the terms that we talk about here. When we talk about fatigue, what we're talking about is we're talking about any loss of mechanical strength that was developed within the contraction. It is not the loss of the want to. That is, it's not where you determine whether or not you actually want to stop the contraction or not. It's about, do I lose any strength within the contraction? In this, we have to remember that we're dealing with Henneman's size principle, in which we're going to be attempting to recruit the muscle fibers, and we're going to recruit from smallest to largest, easiest to hardest to depolarize, where we're going to get this ever increasing level of tension within the muscle. This size principle is also going to be visible when we look at the actual muscle function within the muscle based off of the amount of tension that we're asking the muscle to generate. So we're looking here at a hand grip dynamometer experiment where we're looking at the top line of EMG activity and the bottom line being the strength within the clenched fist. And so if we look, you'll notice that we have this ever increasing amount of electrical activity as we start to have more grip strength. Now notice we don't get this nice single peak line of electrical activity with this nice plateau of grip strength within the clench. The muscle activity in terms of the electrical activity is the recruitment patterning that's going on within the muscle in order to sustain the contraction. But you notice that we have both a larger amplitude and a greater breadth of electrical activity as we have greater amounts of strength being developed. Now, when we look at what's going on within this contraction, what we have to remember is that we're going to have a generalized pattern of recruitment within the size principle that's going to relate between the mechanical force, the strength of the contraction, and the relative fatigability within the muscle fiber, where when we start to contract, we're always going to start with the lowest amount of strength with the least fatigable fiber, the type 1 fibers, and we're going to progress through the continuum until we get to the maximal level of strength that we can develop. But we'll see the highest level of fatigability. That means that we're going to lose the contractile strength quite quickly within those fibers. And this correlates with how easy or how hard is that muscle fiber to recruit. And so whenever we do any type of contractions, what we have to remember is that if we're attempting to do a sustained contraction, we're not going to immediately jump to the greatest strength, highest fatigability, because we know that we have to somehow keep that fiber being recruited. And so what we end up seeing when we have a sustained contraction like we see here is that we're going to see a trepping of the contractile forces going on, where we're going to be varying the summation patterns within the muscle so that we can keep the optimal amount of muscle fiber being recruited in order to allow for that contraction to be sustained. And so if we look at the continuum of effects going on, we start with our normal continuum of effect, where we get the activation from the cortices, where we get the activation from the motor neuron, which leads to the depolarization and threshold at the muscle itself, leading to the voltage-gated channels opening, leading to the excitation contraction couple, leading to the calcium interacting with the troponin, and the ATP cycle allowing for that contraction to take place. Now, what happens is that over time, we're going to start seeing some sort of intracellular and extracellular activity going on, in which we're going to start having alterations of ions around the membrane, making the membrane harder to depolarize. And because the membrane becomes harder to depolarize, it becomes harder to reach threshold. So if you remember back, we start seeing those blips in the EMG activity. All of those blips is where we need additional stimulus in order to get that threshold in order to have the excitation contraction couple. as we start having a change of excitation contraction coupling, what ends up happening is we start seeing a change in the contraction strength. That change of contraction strength is directly proportional to the change of fiber availability. We're going to start losing those high threshold fibers, those large fibers, and we're going to start becoming reliant upon these smaller fibers, the easier to depolarize fibers. This change of fiber availability, leading to the change in contractile strength, is what we deem to be fatigue. So let's take a look at factors that are going to come into play when we look at fatigue. Now, a lot of books will talk about, oh, it's about lactate, or what the books will say is lactic acid, which is not possible because we don't actually form lactic acid within the cell. So what are the actual factors coming into play as relates to the fatigue? Well, there's a whole host of factors that are going to come into play. There is a change of ROS accumulations. They're going to impact the membranes. There's a change of ion concentrations. They're going to impact the membrane. There's an increase of adenosine coming out of the cell. Is going to lead to reduced ability to reach threshold. They'll start having cell damage taking place. We're going to start impacting our energetic pathways. We're going to reduce our CK. We're going to reduce our AK and our AMPK. We're going to reduce our CP. We're going to reduce our glucose levels. We're going to start having factors that are going to inhibit the enzymes. We're going to start having ion issues in between the actin and the myosin interaction. We're going to start to reduce the calcium availability and reduce the magnesium availability, which is necessary to decouple the actin and the myosin. We're going to start having cytoskeletal damage taking place. We're going to start having central inhibitors coming into play, such as changes of plasma ion conditions, such as inflammatory signals like prostaglandin E2, serotonin. We're going to start having thermogenesis coming into play. We're going to start having intracellular inflammatory markers like NF-kappa B. We're going to start having generalized inhibitory signals like adenosine going into circulation. It's these factors here that are causing the quote-unquote pain and quote-unquote burning that we see with sustained muscle contractions or repeated muscle contractions. It is not lactate. Regardless of what people say or how people talk about, the pain and the burning is due to inflammatory responses triggered by prostaglandin, serotonin, and then the burning sensation is due to thermogenesis taking place, not due to acidosis. Additionally, the acidosis that people like to reference as causing the prolonged muscle pain is not accurate as well. The muscle pain that we exhibit from sustained muscle contractions or excessively intense muscle contractions is due to tissue breakdown and the inflammatory signals, not due to lactate.